Okay. Till now we have studied about three different moduli. One was your Young's modulus, one was your what? Rigidity modulus, and one was your bulk modulus. Actually, depending on your dimension or depending on your deformation. Usually we had three kind of moduli. One was your Young's modulus, which was for linear strain. I think we have written Y or something. Linear strain, which was for, and second was for your rigidity modulus, which was for your shearing strain. Tangential force, when the force was applied tangential to the surface, and one when you apply a linear strain, linear stress, or when you apply or when you elongate something or when you squeeze something. And finally we had here bulk modulus, which depended on what? Your expansion or contraction. So today we are going to find the relationship between, it was given by phi or theta angle, basing the angle of strain. So today we are going to find a relationship between these two moduli. Is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
Initially this blue color, can you see this blue color A, B, C, D? Initially A, B, C, D was what? Yeah, was your original cube. It was your original cube. Then what happened? A force was applied tangential to AB. A force was applied to the top of the surface. Then what? Then it turned into what? This rhomboid, basically. A prime, B prime, because the lower, no force is applied on the lower region, only the force is applied on the one of the face. So that's why the deformation will occur over here. Now, can you tell me where is this linear strain? Where is the deformation?
B to B dash.
Yeah. Where is the deformation? Linear, but linearly. Shearing though we can directly see it's over here, phi. The angle has changed. But where is the linear strain? Because linear strain basically deals with what? One-dimensional object. Either it will elongate or it will contract. So which part has elongated or contracted? Any idea?
B dash to C, sir.
Which one? A dash?
B to B dash.
A to B dash, this one.
Yes, sir.
But simultaneously, if you see, this object has also changed. But how does this, usually this change happen? Can you see diagonally it has been changed?
Yes, sir.
Clearly one can see the diagonally it has been changed. And across this diagonal, what? It has been contracted. Initially the length was slightly higher. Can you see this length was higher as compared to this?
Yes, sir.
So actually the linear strain is along this direction, because if you just consider, let's say the deformation happened from, initially it was AB, now it has changed to A prime, B prime. This also one can take. But one has to keep in mind that at every point it will be changing. So you have to take infinite number of points over here, because from this to this and this to this is also different. Let's call it E1, E2, E3, E4. So initially it was E1, E3, which is basically AB. Now it has changed to E2, E4. Can you see that? Now you have to keep, one has to keep on keeping a track of at each and every infinite number of points. So it's better that we take the diagonal, because this will take care of all this deformation. Because diagonally, if you take, it comprises of all the points. So that's why initially it was what? DB. Now it has changed to DB prime. Is this point clear?
Yes, sir.
Also, let me ask you all one question. Now, instead of elongating something, let's say if you contract a certain element, let's say it was initially it was of this size. Now you applied force in this direction. You start squeezing this, and now there is a deformation. Is it different from considering an elongated body if you apply force in this direction? If this is deformation is of same length. Is the question clear? Instead of pulling it, if you push it, at that time also the deformation will occur. Is this two scenario different? Actually, both of them are same because the deformation is of same size. So that's why the elastic property, it will again try to go back to its original position. This will also try to come back to its original position. So here again, why I'm telling you all that is, here you have two choices. Actually, it gets contracted from, if you can see, it gets contracted from AC to A prime C, or either you can take this or either you can take this. So for our timing, we'll be taking this. Now we are finding a relationship between what? Relationship between basically this phi, angle of shear, and linear strain. Linear strain, which is basically what? E. For time being, we'll write linear strain. Now the question is very simple. Now you have to somehow find a relationship between E and phi. Basically, the whole idea is E, you can directly know. What is E? Del L by L, roughly. Change in dimension, or basically it is dB prime minus dB. Change in dimension is that much. Initially it was dB, now it has become to divided by the original length is basically what? Here dB. This is basically E. As you can see, initially this was this, now it's this. Now you have to find a relationship between this and this. So how to go about this? Now actually the deformation is of very small size. Clear? So few of the things we can take some of the assumptions. One thing for sure is we can first, this is not an assumption, we can first draw a perpendicular and write it K. Clear?
Yes, sir.
Now as the phi is very small, now we take this triangle. Now we take this triangle. Triangle B prime K to be isosceles. Isosceles. What is an isosceles triangle? What is an isosceles triangle?
All sides are
Two sides are equal.
Two sides are equal, no? Equilateral are all sides are equal. Equilateral means three sides are equal, no?
Yes, sir.
This is 60, 60, 60. This is equilateral. Now what about the isosceles? Isosceles triangles are something whose two sides are equal. These two sides are equal. Clear? Now let's just consider that reason. Now one thing is BK is perpendicular drawn on KB. That we have to keep in mind. Then we can roughly assume this to be of this form. Now we had drawn a perpendicular, which is for timing, let's do it with this line as green. So it will be easier for you all to see. So green touches with which? Green touches with K and P, that we have to keep in mind. This is actually K, and actually this was supposed to be perpendicular. I think you will understand for a time being. This is K because this has been drawn perpendicular to the surface. This is K and this is B and B prime. This is B and B prime. Now these two sides are, which of the two sides are equal? If you have something like this is a perpendicular, then these two angles should be equal.
Yes, sir.
What should be
Yes,
the
sir.
angle of these two?
60.
This is 90 degree, so this should be, as both sides are equal, so this should be 45 degree and 45 degree. Oh, it should be of 45 degree because this is an isosceles triangle, both sides are equal. So that's why it will exactly make an angle of 45 and 45 with this. Clear?
Yes, sir.
And follow what we can do. dB we can take as dk. What is dB and dk? You can check it over here. dB we can take it as dk. This roughly the amount of elongation, basically we will be taking this. Do you know why we can take this assumption? This also we are taking this as isosceles triangle. This also you can clearly see it's not the case. Because if you draw a perpendicular or, across any point, then what it will be? This will be hypotenuse, will be longer than the base. But why we are assuming that dB is equal to dk? And next thing is, for sure, angle was something like this, and this was a basically k, this was d, this was b. Now we are assuming that dB is similar to dk. We can take this because the angle phi, the angle by which it changes, is extremely small. Clear?
Yes, sir.
As you can see, this angle itself is extremely small. This angle will also be even smaller. This angle will be even smaller. So that's why that is sufficient to take. Yeah.
Yes, sir.
Basically, why? Let's do this. Cos theta. Let's say the angle is of what? Cos theta is basically what?
Base by hypotenuse.
Base by hypotenuse. dk by db. Now let's see. When theta is extremely small, you all start putting when theta is 0, what it will be? Cos theta is how much? For a timing, let's put cos 0.1. Let's say the angle is very small, 0.1 degree. That is small enough. So what will be the value of cos 0.1? You all can try. Do you all have calculator? I'll also try. Let's take some of the values. Cos of 0.1 is how much? 0.1 is 0.9999. Clear?
Yes,
Now
sir.
let's consider the angle to be small. Actually, the angle will be even smaller than this one. So for timing, this much is sufficient. Now, can you see? Can we approximate this as 1? Can we take this as 1?
Yes, sir.
Yes, sir.
So if we take this as 1, then what will happen? dB by dk by dB. Now, can we write dB equal to dk or similar to?
Yes, sir.
So that's why we were able to do this. Clear? Because the angle
Yes.
is extremely small. Now, when the angles becomes extremely small, then we can approximate this too. This will be similar to this one. I think this point is clear.
Yes, sir.
So we'll proceed from here. Now, first thing for sure, you know, one thing is for sure that linear strain is basically the change in dimension by its original dimension. If the diagram was in reference, then it could have been easier for you all. Still, I think it's fine. Now, linear strain you can write in terms of what? dB prime minus dk, basically this divided by dB. Change in dimension, which is dB prime minus its original dimension divided by its original dimension. This you can write. This we have done so many times. This is basically a linear strain. Linear strain. So what we can do after this? Can we write dB as dk? Because we have
Yes, sir.
proved that dB as dk. So let's substitute that over here. This we can write as dB prime minus dk divided by
dk.
dk or dB. Let's put it in terms of dB, okay?
dk.
Or dB for timing, let's put it dB because later it will be easier for you all to. Now dB prime minus dk. Can we check what is this dB prime minus dk? dB prime minus dk is basically B prime k.
No, yes, sir.
Is this point clear? Or k B prime or B prime k if you want to write. Either way, it's fine. Is this
B
point?
prime.
Because we have just substituted that whole length was what? Perpendicular was drawn over here and additional small things comes over here, which becomes KB prime. So this first part is done. This is here equation 1. For a time being, we'll put it like this. And we'll use the second assumption. This angle, can you see how much is this angle? Now,
Yes,
if we
sir.
take cos 45, then what you will get? Cos 45 degree. Cos means basically KB prime divided by BB prime. KB prime divided by BB prime. Actually, this is something like this. So it will be easier for you all. Actually, not. Should be something like this. This is perpendicular. So you are taking cos of this. Cos 45 degree is basically what? This is KB prime. From here, we are taking from here KB prime perpendicular, a hypotenuse. Sorry. This is base by hypotenuse, no?
Yes, sir. B dash by
It should be BB prime by
KB.
KB. Okay. KB prime. Okay, for a time being, let's put it in this manner so it will be easier for you all to see. One thing is for sure, this perpendicular is drawn over here. Then only I think it will be easier for you all to see. This will be 45, this will be 45. Is this point clear?
Yes, sir.
This is B and
Yes,
this is B prime, let's put it, and this is B. Or this is B prime and this is B. Either way, it's the same thing because we have to take. Now we take cos 45 is what? Base is what? KB prime. Because this diagram is drawn in slightly different manner, so it's slightly harder for you all to see. So basically it's what? This is prime. Cos 45 degree is base is how much? KB prime divided by hypotenuse is BB prime. Is it something like this? So can we write this?
Yes, sir.
Yes, sir.
What is cos 45? 1 by root 2.
Sir. 1 by root 2.
Okay, 1 by root 2 is equals to basically KB prime by BB prime. Clear? Or you can write KB prime because we are trying to substitute this KB prime over here. Okay, basically KB prime is what? 1 by root 2 BB prime. And you all know what is dB?
Decay.
dB is from here, from this diagram, can we write? Because dB is
Decay.
just a hypotenuse of this triangle. This was of length L, this was also of side of L. So will it be twice, or let's put it L square plus L square? Will it be something like this? Hypotenuse will be Pythagoras theorem.
Yes, sir.
Just check this blue region. Can you see? Or I'll just highlight this. This, this triangle. So can we write that as basically dB as hypotenuse, which was side was of L square plus L square. Basically it was this one. dB was something like this. dB, this was length L. So the hypotenuse will be what? Square of this two. So this will be basically root 2L. Clear? So now we'll start substituting both this 2 and 3 on 1. Now KB prime we can substitute as what? Basically E is equals to KB prime, we can substitute this one, 1 by root 2 B prime divided by, what is this? This is basically root 2L. So it will be how much? B prime divided by twice of L.
L.
Now why we are doing this much of work only to get this relation? L is fine, but what about this B prime by L? Now we have to find the relation. Now that was our whole purpose of doing this. Can you see? B prime by L now relates this and this. Let me draw it over here, okay? I will just isolate that one. Priming, let's drop this. I think this is not needed. These things are not needed for a timing. Okay. Now finally we are left with certain relation which had B prime and this was basically a B prime, and this was his C, and this is your phi, and basically this is your length L. This was of cube was of each side of length L. So now we are left with certain relation E is equals to what? B prime by L.
Twice of L.
Prime by L, and half is also sitting over here. Now can we isolate this? Now from here one can see. Should we take sine or cos or tan? I think let's take tan, okay? Because tan relates this to B prime and L. Tan theta is how much? Perpendicular by base. Perpendicular is basically what? B prime, and base is what? L. Now, if phi, sorry, this is phi. Now we consider that phi is very small. Much less than 1. Is extremely small. Then what we can take? Tan phi as simply phi. To verify, let's put tan of 0.1. Let's put tan 0.1. So what is tan 0.1? Because it has a relation of sine. Tan of 0.1 is basically 0.001. So actually now if the angle keeps on decreasing, these two numbers will start becoming similar. Now let's do it 0.001. Now, when the angle is extremely small, then what will happen? This two will start behaving in the similar manner because it's sine by cos. So that's why. Because sine will start, phi will start moving across phi, and cos phi will start moving across 1. So that's why we will get phi kind of relationship. Now, when the angle is extremely small, then what we can take? Tan phi as basically phi. So finally, we are left with the relation E is equals to half PB prime. By this, we can write. Now, this is your final relationship. Clear? So finally, we end up with what?
E is equals to half.
E is equals to half of phi. Now we can see this is a relation between
Young.
between linear strain and angle of shear. Basically, what does this mean is, if you take the ratio of this will be similar to half. Now, if you change the angle by phi, now the deformation is of 2e. Can you see?
Yes,
Can we
sir.
roughly take it from here?
Yes, sir.
Now, if we change the angle by phi, we can roughly say that this has been being elongated twice, roughly. Basically, that will be the ratio, but roughly this will be elongated even more. So roughly that is a relationship. Now, if you elongate it further, then it might go even further. Now, is it clear?
Yes, sir.
Yes, sir.
Okay. Now, this was a relation in terms of your what? Your linear straight. Now, for a bulk, it's extremely simple. Now, we are going to do a relationship between now we did this linear strain with your
Angle of
shear. Now basically we have to do linear strain with your what? Volume strain. Linear strain and volume strain. Now this is extremely simple. Now if you have a cube, let's consider, okay? If you have a cube, now if you apply a linear strain or a certain amount of force over here, what will happen? This will start initially, let's say, per timing, let's say is of unit length. Clear? Is of 1 meter, let's say 1 meter. Then after applying force, let's say the deformation is of what? It has slightly changed over here. Can you see?
yes, sir.
Similarly, it will get elongated over here as well. This certain amount of change will occur. Now each side will become what? Basically, now initially if it was 1, now each side will become 1 plus E, where E is here linear strain. Clear?
Yes, sir.
Now if we apply the similar amount of force on 3 sides, then what will happen? Now this is basically increase in one of the side. Now increase in volume will be what? Increase in volume will be basically, initially it was 1 cube. Increase in volume will be 1 plus E whole cube minus side is 1 cube. Because the area or the volume of cube is A cube. A is side. Initially it was 1 cube. Basically how much you'll get? When E is extremely small, then we can roughly write this as 1 plus 3E. An additional term I have just neglected. And this we can write just E. Now the increase in volume is 3E. Now the volume strain one can write as what? Volume strain we can write as what? Increase in volume or change in dimension divided by its original dimension is 1. So basically it's 3e. Now volume strain and your linear strain has a relationship of this. Now this thing is very important. One thing you please keep in mind. Now can you see this is for a three-dimensional object? Exactly for a 3D object, 3 is sitting in front of linear strain. Can you see it?
Yes, sir.
Now similarly for a two-dimensional object, can you see exactly twice is sitting over here?
Yes, sir.
So that's why
Yes,
I was telling you about this is a two-dimensional this is a two-dimensional when you apply on, and this is a three-dimensional. Exactly this kind of relation you will get. Can you see this is twice and this is thrice because this for two-dimensional change in plane. Now this
Yes,
is
sir.
here three-dimensional. So basically what change in volume is basically 3. Now do you have any confusion from here to here? This is just an approximation.
No, sir.
No problem.
No problem, sir.
Basically, what was 1 plus a to the power 1 plus a to the power cube is basically 1 plus a will become what? 3a square plus 3a. Something like this. No,
Yes, sir.
sorry.
Plus a cube.
Plus a cube. Something like this, no?
Yes, sir.
Now, if you take this E is extremely small, actually the volume strain is extremely small. The number is around, let's say 0.01. Now, if you start plugging in 0.01, then what it will be? It will be even smaller. It will be 10 to the power minus 4 or 0.123. It will be something like this. And it will be 3 times of 0.01 and it will be even smaller. So that's why we will neglect this higher order terms. Clear?
Yes, sir.
So that's why we are left with what? 1 plus 3e or 3a. So that's why that is what we have written right over here. Clear?
Yes, sir.
So to summarize, basically we got a relation with respect to what? Your
Volume
shearing
strain.
angle, which was your relation between 2 dimension and 1 dimension. That similarly we got 2e. The angle was because this was for a 2-dimensional, and similarly for your 3-dimensional for a volume strain, it was exactly 3.
3.
So this you can roughly think of this as a dimension. Clear?
Yes, sir.
So okay, that was for today. I think if you have any questions or any problem, now you can ask. Any questions?
No, sir.
Okay, then fine. I'm going to stop this recording. I think it will go to some